Thanks, everyone. We're really honored to have Professor Boris Hanin here, who's an assistant professor at Princeton's Operations Research and Financial Engineering Department. But he works on machine learning right now, and deep learning, theory of deep learning, probability. And prior to Princeton, he was doing similar things as a professor at in mathematics at Texas A&M. But before that, he was here at MIT Math as a postdoc, or here at MIT as a postdoc in math, but he worked on mathematical physics. And I'm lucky to have worked with Boris. We co-wrote a book together about deep learning theory. And yeah, after I'm reminded that after his talk, there will be a reception in the penthouse, and really excited to hear about Bayesian interpolation with deep linear networks. So thanks, Boris.
Good. Okay. Anyway, it's good to meet you all. Okay. So before I start, I just want to say I want to present some very recent work that I'm quite excited about. It's about a circle of ideas that I've been obsessed with for a couple of years, and it's joint with a really phenomenal collaborator, a guy named Alexander Zlokapa. He's a member actually here at IAIFI. He's a PhD student at MIT Physics. So he's great, and he totally deserves equal credit for everything I say. Okay, he's not here right now, he's traveling, or so he told me. Okay, maybe he's just escaping the clutches of his collaborator. Okay, so here's my basic plan. I want to kind of zoom out for just a moment, and I want to formulate what I think are 2 or 3 interesting high-level questions for a theory person to understand modern neural networks. And that'll give me a little bit of an excuse to tell you where I'm coming from, and then I'm going to specialize those questions. In the case of linear networks, I'll tell you what those are, and we'll take it from there. Okay, so here's the start. So, okay, to introduce the subject, let me just introduce some basic notation. Okay, so suppose that we're given 3 things. Okay, just the 3 pillars of doing machine learning. So first of all, we're given a model. Okay, so just think of the model as being a neural network. I'll write f of x with parameters theta, and okay, for our convenience, I will give us something to stare at. Okay, just a fully connected network with some nonlinearity sigma, some weight matrices W1 up to WL+1. I think of this as capital L hidden layers. Okay, and because I'll use the notation in a moment, my weight matrices, the one in layer L, have the following dimensions. They're NL by NL minus 1. Okay, that's my excuse for telling you what the widths of my network are going to be. Okay, so this is the first thing we're given. We're given a model. Okay, so the second thing is we're given a data set. So maybe I'll call it script D, and it's just a collection of observations. Maybe I'll write it down here, X, I, Y, I. Okay, I goes from 1 up to P. So these are my training data points. Capital P is the number of samples that I get to observe. Okay, so I have to have these 2 things, and then to actually do learning, I need a rule to do learning. So that's the third thing I'm going to be given. Okay, so a learning algorithm. So I'll just generically call it script A, and what does it do? Right, it takes in the model and the data set, and it returns for you some setting of parameters. I'll call it theta learned for the model. And you use this to make predictions. And this is basically how supervised machine learning works. Okay, so this is the general context. And what I want to do is I want to formulate 3 questions that I'm broadly interested in. I think a lot of people are. And I'll try to give you answers to those questions in a particular case in a moment. Okay, okay, question 1, and I will kind of give light annotation to why I care about these questions in a moment. Okay, so for me, it's like this. What are the joint effects of taking large the 3 parameters we have? Okay, P and the widths and the depth. So somehow when I think of machine learning models, one way you can think about them is as a model that has many large parameters. Okay, typically our networks are large, so maybe the width is large, maybe the depth is large. Certainly our data sets are often large. And we want to know what are the joint effects of these 3 parameters. And just as a kind of cautionary tale, okay, one of the reasons it's both interesting and hard to answer this question is that the limits where you take these parameters to infinity don't commute. That's why it's not so simple to study. Okay, so I want to harp on this point. for just a second because it's going to set up the rest of what I try to say and why I was excited to be able to get some kind of analytical answers. Okay, so here's like two very simple, but I think kind of hopefully insightful pictures. So let's first think about the very simplest case where you take 0 hidden layers. So just literally a linear model. And in that setup, you only really have 2 parameters, right? You have the number of samples and you have the input dimension and 0. Okay, so classical statistics tells us the following thing. So suppose you observe a model that has 1 million data points that live in 1 million dimensions. And you try to understand what are the properties of this large scale model. Well, okay, so if you don't know how to do high dimensional statistics, you could think naively of 2 possible answers. Okay, you might say, look, well, I have 2 large parameters, and maybe I can think of it like this. Maybe I can think of the input dimension as being infinitely large, and I can take the asymptotics at large p. Okay, so I take p, I send n0 to infinity, and I ask what happens as I go up to this model. So maybe that's a good approximation. But then you could say, wait a minute, why not do the opposite, right? You could fix the input dimension and take the asymptotics as the data set size goes to infinity. And maybe this is a good approximation to what happens. And okay, one of the fundamental points in modern statistics is that neither of these 2 is a good approximation to what happens at all, and they're not close to one another. So really what happens is this is all very bad. You should never draw this picture. In fact, you should delete these as well. These are not the things to compare against, right? There's a 1 parameter family of models where the interpolating parameter that basically goes along these straight lines is the ratio of p over n naught, which starts up here at being 0. That's the regime where the input dimension is much bigger than the number of samples, and p over n naught equals infinity over here. And really, the nice limiting model is you compare to the case p over n naught equals 1, and they're both large. That's how you're going to get high fidelity predictions. Okay, so this is what I mean. Like, I'm a mathematician by training. So when I say the limits don't commute, I just literally mean taking one to infinity, then the other gives you a very different set of answers than the opposite way. Okay, so this is like what happens with p and n naught. But now in neural networks, it's even more complicated because we also have the depth of the network to deal with. And it turns out that the depth also doesn't commute with these parameters. Okay, so here I have to give a shout out to Dan. So Dan is one of the world experts on this particular question. Okay, we did a bunch of work on this together, and I love these kind of things. So here, think of like p as being finite. Okay, and think of on the x-axis now being the depth of the network, and here being the widths of the hidden layers. So it turns out, although it's not completely obvious, that a very similar picture is true. If you want to understand neural networks that are both deep and wide, then it's not enough to fix the depth and send the width to infinity and then study large L. Okay, really the right thing to do is a very similar looking picture. You have to make a phase diagram like this. You introduce a new kind of effective depth parameter, which is L over n is equal to a constant. And it's really this value of the ratio of the depth to the width that determines what happens. Okay, so this is why, like, I think this is an interesting question, and it's not completely obvious what the answer is going to be. Like, how do all these large parameters come in to give an effective notion of what the model is supposed to be doing? Okay, so I'm going to try to answer that question in a moment. So that's kind of question number 1. Okay, so question number 2, I promise the last 2 questions will have less commentary. So one of the main issues that makes it difficult to understand models like neural networks is that they're not linear models. So more precisely, the question is how to analyze the properties of the learning algorithm A when the map from the parameters to the model is nonlinear. Right? So if you had a linear model, there's a very well-developed set of techniques that, okay, for me as a mathematician, come from analyzing certain kind of Hilbert spaces called reproducing kernel Hilbert spaces that underlie the kernel for your method. Okay, there's some like nice mathematics that tells you how to analyze a variety of learning algorithms. But when things are nonlinear, it's a little bit hard. And this is like a fundamental challenge people have to face when analyzing neural networks. So that's question number 2. And then question number 3 is to try to make sense of the idea of feature learning. One of the reasons neural networks are so powerful is that they're nonlinear. and they somehow learn features or representations. These are words people use all the time, but it's not 100% clear sometimes what exactly is meant by those words. Okay, so I'll write it this way. Well, quote unquote features of the training data or of the statistics of the training data are encoded in your learned parameters. Okay, so somehow like having some clear language around these questions for me would be great as a general step in understanding nonlinear learning. And what I want to do is I want to present answers to these questions in a particular case. Okay, so maybe I should just stop for a second and see if there are comments or questions, because this is kind of the end of the motivation. So if it's not clear why I'm doing what I'm doing, it doesn't matter what I'll say later. Anyone have a comment or a question? Yes, please.
Call these phase diagrams. Can you just say a little bit more what you mean about the regions in these diagrams?
Yeah, okay, so potentially phase diagrams was a bad choice. Okay, you have to remember I'm a mathematician. I don't really know what I'm talking about. But okay, to give a somewhat less glib answer, let me put it this way. Imagine that you, for a second, just fix your training data set size. I don't think about that as being large. And you ask the question about what happens if you take a model in which the widths and the depth both go to infinity. Okay, but the widths go to infinity much faster. So you're going to end up somewhere like you're going to basically approach this corner of the diagram, or if you fix the depth, you're going to be just going to a point up here. So one of the upshots of the work that I did together with Dan is the idea that everywhere up here, L over N measures the effective depth, L over N equals 0, and you get linear models. Okay, so there are some caveats around this that are important. So this is like a measure of effective depth. You get linear models. If you've ever heard of the NTK or something like that, this is the idea that in a certain asymptotic regime, neural networks can just be replaced by their linearization, and that's all they do. And so it's somehow like this is a better measure, L over N, of how deep you are than just the apparent number of layers. That's the kind of thing I mean to evoke with this diagram. So I hope that kind of answers the question. Yeah, great, thank you. Good, I should have said that, but I didn't. Okay, there are some caveats about, depending on how you initialize, if you have like not MLP type architectures, you get different answers. There's a whole beautiful world of people who do that. Okay, other questions? Okay, very good. So let me tell you what I want to do. There's my plan for the talk. Okay, so I want to answer these three questions. In the simplest context that I know of where it makes sense to ask all of them. Okay, so I want a context in which I can change the number of samples, the width and the depth arbitrarily. I want my model to be a nonlinear function of its parameters, and I want to have some kind of feature learning that I can exactly get my hands on that I'll tell you about. Okay, so specifically it's for these deep linear networks. So here's my setup. I take the nonlinearity and I just set it to be the identity. Okay, so in your neural network, the sigmas are just gone. You just have a product of matrices. And I take the output dimension and I set it equal to 1. Okay, so in this model, f of x theta is just a product of matrices times x. So these are called deep linear networks because they're linear in x. Okay, but they're not linear in their parameters W1 up to WL plus 1. Yes, please.
Yeah, sorry, can we move back a little bit? So you didn't say anything about learning these limits. So
I'm about to tell you what kind of learning. So there's different kinds of learning you could do. I'm about to tell you what learning I'm going to do.
Yeah, I mean this phase diagram after the learning done.
Okay, right. So here the phase diagram, the learning is minimal norm interpolant, let's say. Okay, you have a linear model. That's how you do learning. So for this phase diagram in the book with Dan, this is training with gradient descent. Also, it's true for training by Bayesian inference. That's what I'll talk about in this model. So there's different kinds of learning, and at least for the ones we know how to analyze, L over N is the operative parameter.
Okay, I'm just thinking in case when we train generative model with reverse scale, for example, where we have in some sense infinite number of samples, where we have infinite number of steps, right? So the limits are connected. Right,
so that's fair, and these are just questions, right? And I'm going to be extremely specific right now, hyper specific about what I can prove. And beyond that, I'd rather not speculate because who knows? that's sort of my feeling. Okay, so f of x theta looks like this, but I'm going to write it nonetheless. I'm going to collapse all the matrices into a vector theta, right? Since I assume that the output dimension is 1, this product is just a vector. And I'm going to think often about things as a function of this vector theta. It's going to be more convenient. Okay, and then script A is going to be Bayesian inference. Bayesian inference, and I'll tell you exactly what that means in a second if you don't already know, at 0 temperature. Okay, so to do Bayesian inference, I have to give you a prior on the parameters. So it's exactly the usual prior that one takes. So theta is drawn from the prior distribution on theta. If and only if the entries of these things are independent Gaussians. Okay, so WL, IJ are Gaussian, mean 0, variance sigma squared over NL minus 1. Okay, so all the individual entries of the weights are independent Gaussians. They have the correct normalization in terms of the dimension of the matrices, and there's a single scale parameter, sigma squared. So although the individual distribution of the W's before training is very simple, the product is rather complicated. Okay, so that's what makes this a kind of nonlinear model. Okay, and then the loss function, or the likelihood that I take, is the one you normally take for linear models. It's just theta transpose times your data matrix minus y squared. In other words, it's the sum over your samples of the prediction on the sample minus what you're supposed to get squared, just the mean squared error. Okay, I don't put a 1 over p there. Yeah. Yeah, so right. I will tell you, so I'm going to tell you everything about this prior because I'm in fact going to compute the posterior as well. But the point is this, the prior is not such a simple thing, right? Because when you take the product of all these independent Gaussians, every entry of your vector theta ends up having correlated entries because the same things participate everywhere. So you get something that I'll draw in a second is rotationally invariant just because the first weight matrix is rotationally invariant. But like the components are not independent. So it's some complicated distribution.
This is a definition.
This is the definition of my prior. So just think of this as the initialization before training. It's just I'm not going to train by gradient descent because I don't know how to do the calculation. Okay, maybe ask me in 6 months and I'll tell you how to do that. Maybe. Okay, I can't guarantee it. Okay, so this is my claim, at least in this model, which is much simpler than the general nonlinear case because you can only learn linear functions of x. The flip side is you're going to have like 3 takeaways, which I at least found to be exciting enough to try to write a paper about. So my plan is I want to briefly formulate the 3 takeaways, and then I'm going to try to draw some pictures and give a sense of what the prior and posterior look like, and then I'll state theorems eventually. Yeah, please.
Where's the temperature?
So I'm about to tell you. Normally, you put the temperature in front of this. So temperature 0 means I'm going to look at posteriors which insist on exactly minimizing the loss. So it's like taking your prior and conditioning it to the space of things that fit the data.
If you're doing Bayesian inference, do you think that there are people online? Since you're doing Bayesian inference, I guess normally we think of losses when we're just optimizing a function. I mean, you really just mean like negative log likelihood or something.
Yeah, that's all I mean. That's right. That's why I call it L for log likelihood. You thought it was a loss, but that's because you're an ML person. No, you're right. You're right. It has the same kind of interpretation. Good. Okay, so here are the 3 takeaways for me. All right, so point number 1 is that this setup, so Bayesian inference with deep linear models is exactly solvable. So I don't have to take any limits to infinity. I can just write down a formula for the posterior, and I hope I'm going to have time in this talk. I'll write it down for you. Okay, so when L equals 0, when you just have one weight matrix and you have a linear model, this is like a totally classical fact, right? If your prior is Gaussian and your log likelihood is quadratic, then your posterior is also Gaussian. Done. That's like the basis for almost all like exact Bayesian inference in practice. But it turns out you can actually write down the posterior here too, and I don't believe anyone knew that. Okay, so that was like kind of amazing and exciting for me personally. Okay, so takeaway number 2 is an attempt to answer this question. So I already sort of hinted to you that the way that the depth couples to the width in these models tends to be through the ratio of the depth to the width. and that the way the number of samples couples to the width is something like the number of samples divided by the width. And it turns out that there's a kind of nice generalization of this. Okay, so the effective depth of the posterior that you get looks like this. So it's the sum of the it's the number of samples times the sum of the reciprocals of the hidden layer widths, which you can just think of as P times L over N. So I didn't know what to expect, but it turns out there's like a single parameter that controls the structure of the posterior, and it's built out of the number of samples, the depth, and the width of the network in this particular and slightly peculiar way. Okay, so if you've ever heard of like scaling laws for neural networks or something like that, I'm just saying this gives you polynomial type dependence for various properties of your network after you do Bayesian inference. And it shows you kind of how P and L and N play together, at least in this very simple model of linear networks. Okay, so I was really excited to see how the P fits into the story. And now I have my answer in this case. Okay, and then takeaway number 3, and I promise I'll state exact versions of this in a moment, but that's going to be rather mathematical, and so I rather say it at least informally first, is trying to explain something about feature learning, and that's really the first thing I'll try to draw for you when I write pictures. But it goes like this. It says, if you take deep networks plus universal priors, so it actually will turn out when I say universal, the right thing to do is to take sigma squared equals 1. That's actually the thing you have to do in practice. Okay, and Dan and I worked that out in our book as well. There's some reasons that sigma squared equals 1 is the best thing to do. But so you can take very deep networks in the sense that this parameter is large with these universal priors, give exactly the same posteriors as fixed networks, so shallow networks, but with the optimal data-dependent priors. Optimal data-dependent priors. Okay, so one thing that you're allowed to do when you do Bayesian inference is you can ask, what's the best prior to take? In this context, it's very simple. What's the best value of sigma? Sometimes people call this empirical Bayes. Okay, you grab your data and you say, okay, cool. I want to estimate what a good prior is to use by observing part of my data set. And then you try to estimate the value of sigma squared that maximizes the partition function, which I'll write in a moment. It's called the Bayesian evidence in this world. Okay, and then the posterior you get turns out to be this universal posterior that doesn't care about the particular architecture you chose. So you could take the best data-dependent priors and do Bayesian inference, but you get the same exact thing as just taking sufficiently deep networks and taking universal data-agnostic priors. Okay, so this is like some humble version, at least in this very specific model, of the statement that in practice we kind of know to be true. By taking deep and wide networks, you learn good features. In this case, you learn optimal features from data-agnostic priors just by shaping the network to be sufficiently deep. Okay, so I'll state some exact theorems about that, but these are the 3 things that I feel like I learned at a high level.
Sorry, when you said features there, are you going to say precisely what you meant by learn good features?
Yeah, I am. I'm about to say that right now.
Awesome.
Right. Yeah. So Dan. Okay, you're right, Dan. You caught me out. I'm a little vague, but that's another reason I like these linear networks, is that I realized that in this model there's a very precise notion and rather simple notion of the feature learning that they're capable of doing. So I'm going to tell you about that right now. All right.
So can you hear us?
Yeah.
Oh,
yes.
Okay. You could hear us from Zoom. Yeah. So when you talk about the effective depth, why is that inverse with the width? That's not technically the depth. If I mean intuitively, if it's wider, then it's better. But you're saying actually the effective depth is inverse of
well, what I'm saying is that if you take a sequence of linear networks where this parameter, number of samples times depth over width, goes to 0, you will have exactly the same posteriors you get from a linear model. That's the sense in which sending this to 0 gives you depth 0. And it turns out, moreover, that the posterior is completely determined by this one parameter. And as it goes off to infinity, you get these optimal data-dependent posteriors that I'll talk about. Okay, so like it's a bit of an interpretation to say it's the depth. But once you realize you're not sure what the depth is, then I think you're free to make an interpretive. I mean, so it's a fair question, but I hope that when I state things a little more precisely, you'll be happy. And if not, you should ask me again.
Yeah, I mean, I asked this mainly because I was familiar with the kernel methods with infinitely wide networks, and there it's actually hard to show the learning is better with that.
Right.
Maybe you have a different notion.
So that's one of the reasons I'm excited about this work. I'm going to show you that, in fact, you need depth to do optimal feature learning. It's like a precise version of that statement. It's like a theorem. Okay, so let me draw this picture, and I will hopefully answer your question about what optimal means, and then you can ask me again if you don't believe me, because I think that's totally fair. Is that okay? I just don't know who is.
Yeah, thank you.
Yeah. Okay, so let me tell you something about the structure of the posterior. Okay, so for this, I think even my picture drawing abilities should suffice. Okay, so here's how I think about it. So let me remind you that the model in the end looks like this, right? It's just theta transpose X, where theta was the product of the weight matrices, just for notation's sake. So I'm going to write this in the input dimension space. So theta and X are both vectors in this Rn0 space. Okay, so what do you have? All right, so you have a space of interpolants, and I'll call it script I. This is just the hyperplane. It's those thetas that exactly match the data. Okay, very good. So always in this kind of model, I'm going to be over-parameterized. So you have an infinite number of ways to fit the data exactly. And when this happens, there are two interesting directions. Okay, this is like basic fact in linear algebra, in which this space is partitioned, right? So these directions here are the span of the training data points. And these directions here are the orthogonal complement to the span. Complement. And indeed, if you take a general vector theta, you can decompose it into its projection, which I'll call theta parallel, which is the component of theta that's responsible for actually fitting the data, and theta perpendicular, which is the component of theta which is orthogonal to all the training data and therefore doesn't affect your loss at all. This is like the basic linear algebra of underdetermined systems of linear equations. Okay, but this picture is going to tell us a lot about the structure of the posterior. So let me build it up little by little. So the first thing to say is that the prior on theta is radial. Okay, this was really already part of what I told Jim when he was asking me. And the reason is that, okay, this is just the prior, right? The first weight matrix, this W1, is a Gaussian matrix, and so it's rotationally invariant. Okay, so you can think of the thetas under the prior as being drawn from some rotationally invariant distribution. But the trouble is that although it's rotationally invariant, the norm of theta is a complicated distribution, which I'll get to in a second. Already, this is nice though. Okay, so now I can tell you exactly what the posterior is, and I'm going to write it out in detail because I want to emphasize something about it. Okay, so by definition, the posterior on theta depends on your prior. I'll just write as sigma, depends on the model, and depends on the training data, right? And it looks like this. So I'm going to leave a little room because I want to take the zero temperature limit, but it's the prior distribution on theta, which depends on the prior and the model, times the likelihood. You have e to the minus beta times the log likelihood of theta. So beta is your inverse temperature parameter. And then you have the partition function, z beta, which is the probability of observing your data given the model. I should put a sigma. Right, so for physicists, this is the normalizing constant, the partition function, but the Bayesian inference people have a special name for this. This is called the Bayesian model evidence. This is the probability of observing the data set that you see given only the model. And so maximizing this denominator is a way that Bayesians do model selection. When you maximize this, this is just doing maximum likelihood estimation over the space of all models. That's like a classical thing to do. But okay, so I told you I'm doing zero temperature, so I'm going to take the limit as beta goes to infinity. Okay, and when you do that, the point is this, right? The prior is this thing I already drew. It's this rotationally symmetric distribution. The negative log likelihood at finite beta is a Gaussian bump, which is centered at the space of interpolants. And by taking beta to infinity, all you're doing, if you don't care about the denominators, this is just proportional to the prior distribution of theta conditioned to theta lying in the space of interpolants. Okay, so mathematically speaking, it's very simple. Like on the level of this picture, you take a complicated prior and you want to compute its conditional, and that's the posterior. That's all I'm aiming to compute. And that's what I mean by my learning algorithm A. That's what I'm able to analyze. Okay, so let me pause for a second and ask if that's okay, because with this notation, I can point out to you that the structure of the posterior is shockingly simple. Okay, so if this is all clear to you, you can try to beat me to the punch. See if you can figure out that there's only 1 degree of freedom in the posterior. That looks a little shocking, but it's true. Okay, is there questions or comments about this? Are you happy with this picture now? I'm going to pick on you. You're happy with the picture. Okay, so let me now make completely precise what feature learning means in these deep linear networks. And here's the upshot. Okay, so I'm going to write it like this. So the observation is, okay, if you draw theta from the posterior, so here's my claim. So, okay, first of all, what do you know? Okay, let me go back down here because I can't help myself. Right, so if theta is drawn from the posterior, I told you that the posterior is supported on the space of things that fit the data. So that means that theta parallel, this parallel component, has to be exactly equal to the minimal norm interpolant theta star. Okay, so theta is equal to theta star. Okay, plus you can always take the other component and you can write it as the norm of theta perp times the direction of theta perp. And that's a legal operation that I wish my students would learn. It's a good trick. But okay, here's the key observation. There's a very large amount of symmetry in this problem. Namely, note this. So the prior is rotationally invariant. So in particular, under the prior, this direction is uniform. But the likelihood is independent of theta perp, right? Theta perp does not go into whether or not you fit the data. And so what you learn is that this thing here is necessarily uniformly distributed on the unit sphere. I'll just write uniform on the sphere. Okay, so the upshot is that there's only one parameter you're allowed to learn. So this norm of theta perp is a learnable data dependent or potentially data dependent scale. If we're making predictions in directions that are not in your data set on new directions. Okay, so what I mean is this: if you take a test point and you do f of x theta, theta is sampled from the posterior, what do you know? Okay, well, you know that in the directions that are already in the span of your training data, you have to just do exactly what the data tells you because you fit the data exactly. Okay, plus you get this scale, which is allowed to depend on the training data. And that's what feature learning is going to all be about, using observations in the directions that you know to make the correct scale for predictions in directions you haven't seen. Okay, times a uniform random vector. So I'll write it like this: theta over norm theta transpose x perp. Okay, so this is always the same. This is always the same, but this dictates the scale of predictions in directions you haven't observed. Okay, so these models are very humble in their own way. They can only learn to do one thing. They can say, I'm going to observe the labels y in the directions that I've seen, and I'm going to try to do something sensible about making predictions in directions I haven't seen. That's all they know how to do. Okay, that's the structure of the posterior, and that's why there's only 1 degree of freedom. It's just the distribution of this one random variable. Okay, very good. Great. How am I doing on time? Okay, I'm doing fine. Okay, so it's now time to try to state some theorems, but let me again just pause for 1 second and see if this is okay while I erase. I want to at least get some rigorous results on the board.
Well, while you're erasing?
Yeah.
Is it obvious that theta perp just doesn't want to be 0?
No, it's not obvious at all. Sometimes it will want to be 0.
And it's something about the data set that will tell me
Well, so you see, right. So, okay, great. That's a great question. So theta star knows not only about the x's, but about the y's. That's the crucial thing about theta star, because you have to fit the data. So if all the y's were 0, for example, theta star would be 0.
Mhm.
And so maybe you do want to make 0 predictions in directions you haven't observed.
Mhm.
But if it's non-zero, then it doesn't sound like a good idea. So it's like, it depends on the data that you have.
Got it. Okay, thank you.
Does that kind of make sense? Yeah, okay, cool. All right. Very nice. All right. So let me try to state a theorem first. So I erased the 3 takeaways, but I'm actually going to talk first about this optimal feature learning thing. That's the first thing I'll state a theorem about, and then I'll tell you about the exact formulas a bit later. Okay, so here I go. So for L greater than or equal to 0 and NL greater than or equal to 1, let's do empirical Bayes. Okay, so this tells me I fix my architecture. I tell you how many layers you want. You're allowed to have 0 layers. You can't have -1 layers. I don't know what that means. Can you have any width you want? And I'm going to ask, what is the best prior scale to have chosen? What's the best sigma? Okay, so the way a Bayesian would do this is you would say, okay, at least I'm going to take the limit of large data to do this. So as I observe more and more training data points, okay, so you have to take number of training data points and the input dimension to infinity, and I'm going to take them to infinity at a fixed ratio alpha naught. I'm going to find the argmax in theta of my partition function, z infinity of the data, given theta L and L. Okay, so this is literally the value of the prior that maximizes the Bayesian evidence, or that maximizes the partition function. Yeah.
Sorry, I can see how for control you just want to take P to infinity. Could you comment on why you want to take the data dimension to infinity?
So because as I already mentioned, what happens is the answer depends on alpha naught. So you're free to take alpha naught to 0 if you'd like, and you'll the whole theory will work just fine. But like each value of alpha naught corresponds to a different theory. And so I'm saying this theory works for any fixed value of alpha naught you like.
Got it. So alpha naught is a parameter that just emerges naturally in considering.
That's right.
Theory.
So when you compute this limit, what you find is that this answer depends on 2 things. So maybe I should say it. Sigma star is a function of alpha naught and a function of the norm of the minimal norm interpolation. So again, I should also say of the architecture you fixed. These are just fixed. So you just get an exact formula in terms of this. And so if alpha naught is 0, okay, you get a formula for it.
Got it. Thanks.
Yeah, great question. I should have said that. Okay, so this is the first thing you can do. And then what I want to say is the following. So then if you actually were to go back and use this most likely value of the prior to do your Bayesian inference, what you're going to find is a universal posterior. Okay, so the limit as P and N naught go to infinity, at the same fixed ratio, they go to my favorite constant, alpha naught. And I'm simply going to report to you the posterior over this one parameter, because that's the only thing you need to know the posterior, the only thing you can possibly learn. Okay, so this is the posterior distribution of the norm of theta perp squared. Okay, given sigma is equal to sigma star, okay, and your architecture. So it's equal to a delta function on a particular value that I'll call k star for no good reason. Okay, there's a particular value. I can write it down for you explicitly. It's not that important for what I'm about to say, but there's like a universal posterior, which is independent of your architecture, which says if you were to just choose the right sigma, you're always going to prefer to make this scale of predictions. And it's exactly the kind of thing you were saying, Jesse. You know, you basically say, well, cool, if my typical y is twice as big as my typical x, I should probably be doing the same thing in this direction. That's all this kappa star is going to record for you. Okay, and this kappa star depends on alpha naught and the norm of theta star, but it doesn't depend on the architecture. So this is one thing to say. There's a kind of universal preferred posterior if you're willing to take data-dependent priors. But typically in ML, we don't take data-dependent priors. So okay, that's good. Math to the rescue. Okay, so moreover, let's do the other thing. So let's suppose that we allow ourselves to scale the model together with the data set size. Okay, and we're going to do it like this. So we're going to take the ratio of P of n naught to go to the same alpha naught as before. And then this P times L over n to go to some parameter lambda. Now you allow this to be whatever you want. Okay, so what do you actually get? So then it turns out that, I'll just write it this way, the posterior over the norm of theta perp squared converges to a delta function on this magical value kappa star times, okay, I don't know what to call it, I'll call it z for no good reason, a function z of lambda and alpha naught and the norm of the minimal norm interpolant. Okay, where the key point is the following, this function does the following. Okay, so this converges to 1 as lambda goes to infinity. Okay, and it converges to, yeah, I'll write it this way, the L equals 0 answer divided by kappa star as lambda goes to 0. Yeah, sort of a brutal way of writing it. But like, sorry, yeah, it's very good. I should specify here. The point is that sigma squared equals 1. Okay, I missed the most important point. Sorry, let me say this in words because I got too excited. So I'm saying, instead of taking these very carefully tuned data-dependent priors, just take the data-agnostic prior, which corresponds to sigma squared equals 1. Okay, but let your model grow the depth and the width and the number of data points all go to infinity, and this effective depth goes to some number alpha. And this ratio goes back to the same number, sorry, to lambda, goes back to alpha naught. Okay, then the point is that you always get that your posterior distribution of the scale collapses to a particular preferred scale. And moreover, if you were just to take lambda to infinity, so if you allow this to actually diverge, you will get exactly the same posterior as you got by maximizing the Bayesian evidence. Okay, so that's like my precise statement that deep networks learn optimal features from an agnostic prior. Okay, that's like, that's the statement in all of its glory. And of course, this is like literally a theorem only for these linear models.
Is this PL over N the unique parameter that has this property?
Well, I don't know what that means in the sense that we compute this posterior explicitly, and it depends only on alpha naught, the norm of the minimal norm interpolant, and PL over N.
So it just emerges directly from the model, and you see that this parameter in these two
That's right. That's right. So you don't put it in any way.
Okay.
But it wasn't obvious to us that it was going to appear. Somehow that was part of the fun of doing the calculations. It kind of like, okay, you get it, and then you scratch your head, and first you get the wrong parameter, and then eventually you correct it and you get the right parameter.
Thanks.
Yeah, for sure. Okay, very good. So this is the story about the optimal feature learning. Okay, so feature learning in the sense that you learn the best predictions in directions you haven't seen. And for me, this was like kind of fun because it's a slightly unusual notion of feature learning. It's not what I normally think of as like making data-dependent predictions. Like I think of feature learning often in terms of basis functions, but okay, somehow this is the thing that we thought was most natural here. Okay, so I want to state one more theorem if I can. And then if I have time, maybe I'll state even another one, but probably I will refrain from doing that. Okay, so here's one more theorem. Okay, cool. So I told you that this model doing Bayesian inference with these deep linear networks, okay, at 0 temperature, with all these assumptions, exactly solvable. So then it like raises the question of what does it mean that a model is exactly solvable? Like what constitutes an answer? Right? You could just say, well, Bayesian inference is well defined. There's just a bunch of integrals. No, of course, that's not what I mean. Okay, so let me tell you. Okay, so to describe the posterior, I'm going to introduce this kind of like, okay, I think of it as the characteristic function, but it's some kind of like decorated partition function if you want. Okay, so it's the expectation under the posterior. I introduce a dual variable t, and I call this z of t. Okay, so the distribution of the posterior is uniquely characterized by this generating function. So I'm going to tell you about that. And here's what you get. So believe it or not, there's just a formula for z of t. And I'm going to write it, and you might be slightly horrified. Well, okay, it depends who you are. Either you're going to love it, or you're going to say, oh my God, I can't believe anyone wanted to derive that formula. Okay, but here it is. So, okay, you get an explicit constant, which I will not report unless you're desperate to hear about it. And then you have a simple e to the I theta star transpose t parallel. So you take this vector t, it lives in the same space or in the dual space if you want to theta. So you can decompose into theta parallel and theta perp, t parallel and t perp. This is the fact that you have to fit the data. Okay, and then there's an interesting thing. So this, I'll write it up here, times, very good. So here I go. You get the sum on k goes from 0 to infinity. Okay, so you get minus the norm of t perp squared times a certain constant m to the k over k factorial. Okay, times, well, okay, here we go. Here's where all the bodies are buried, so to speak. So you get, I'll tell you what this is, this certain kind of special function called a Meyer G function. Okay, it's like a vast generalization of all the special functions you know mostly, Gaussians, trigonometric functions, Bessel functions, whatever. It takes in 4 integer parameters here. It takes 1 complex parameter here. Okay, so it knows about the data through the norm of the minimal norm interpolant divided by 4m, turns out. And then it takes in L plus 1 more parameters down here. So this bar means there are no parameters. Not that it's really human interpretable what I'm saying here in a sense, but I'm going to tell you the definition in a moment. Okay, so first, let me just say, I'm going to tell you what M and G are in a second, but this is the complete formula. This is like an identity. Okay, there's a constant, right? And if you want to know the correlation functions of your posterior, you just have to differentiate Z some number of times with respect to T and set T equal to 0. And this complicated looking term doesn't have any T's in it. They're just some constants that tell you about the dependence on the data, and they tell you about the dependence on the architecture. You know, there's like number of data points, there's the width of the first layer, width of the nth layer. It's just some complicated looking constants. Okay, but let me be slightly more specific. Okay, so just to show you that I can, so to speak. Okay, so M is the product on L goes from 0, little l goes from 0 to capital L of sigma squared over NL. So that's, okay, that's what it is. And these G functions, each of these is just a single contour integral in the complex plane. Okay, it's not such a bad contour actually. So you take G little l 0, 0, L at Z, okay, with parameters B1 up to BL, it looks like this. Maybe I'll write it here. It's 1 over 2 pi I, the integral from minus I infinity to I infinity. So it's just an integral over the imaginary axis of a product of gamma functions. J goes from 1 up to L, gamma of 1 minus Bj plus S. Okay, all of this times Z to the S ds. Okay, so I'm pleased because the formula fit on one board. Okay, so what I'm saying is, look, I mean, in the end, this doesn't look like the most pleasant formula, but you have one sum to compute. But if you only want, let's say, the like 100th connected correlation function, you only need the first 100 terms in this sum. And in particular, you just have to differentiate with respect to these t's. That's easy. And each one of these coefficients is just a single contour integral. Okay, and when you work hard enough, you do it by some saddle point method. It turns out there's some nice deformation. You apply some changes of variables. And what we do under the hood is we compute asymptotic expansions for each one of these integrals. We plug them back into here, and then we actually take limits in whatever regime we want, and we see what comes out. That's pretty much how we solve these models. Okay, so let me stop here for just a second and ask if there are comments or questions.
Is this on? Okay. Can you shed some light on how any kind of symmetry is present in the data structure, like Z2 symmetry or permutation symmetries would show up in the structure of Z as a function of T, and also in the limiting points alpha 0 you have in the board above?
Right. Okay. So that's a great question. So let me make two remarks. So the first thing is, notice that because your prior is rotationally invariant, the only thing that can ultimately matter is the norm of the minimal norm interpolation. So you can rotate your data however you want. You're not going to see any structure like that. Okay. And indeed, the only thing that really appears here is the norm of the minimal norm interpolant inside this G function, and everything else is determined, okay, except for the actual value of the minimal norm interpolant for making predictions in directions that you've already observed. So in that way, no like intricate structure of your data in terms of rotations can be seen. But the other thing to say is that the only thing that matters from your data is just the minimal norm interpolant itself, or basically just its norm. And so if you have any two data distributions, and then you ask, what's the statistics of the norm of the minimal norm interpolation? As long as those match, you're going to get the same answer. These models cannot distinguish between. Okay, so some kind of permutation variance isn't really going to affect something. So like I said, these models are slightly humble, and the reason is that, like, they're still linear in X. You get the space of linear models, and you're parameterizing it in a funny way. That's kind of the thing you're doing.
I see. Thank you so much.
Yeah. Okay, so let me make just one more remark, if I may, about this. Okay, so maybe two remarks. I can't help myself. Okay, so when L equals 0, G1, 1, or 1, 0, 0, 1 is just e to the minus x. Okay, so you recover the fact that when you have a linear model, your posterior is Gaussian. That's like a nice thing. The other thing to say is that there's a really awesome group. Okay, I should have given them credit before, but let me just say this. The fact that the prior distribution on theta can be written in some way in terms of these G functions. Okay, I'll say M and PQ because they're a little more general, was done by a really great group at Harvard led by Cengiz Palavan, who you guys potentially know, but his group is awesome. And what they basically realized is that this complicated prior, I forget who asked me about it originally, when you take the theta to be generated by a product of independent Gaussian things, has an exact formula in terms of one of these G functions. But then what they didn't realize is that actually all the operations needed to compute the posterior, if you just go open a book on special functions, okay, you'll find 200 pages of formulas about G functions. And somewhere, if you pick the right 18 formulas, you can compute this thing exactly starting from the prior. Okay, it just wasn't obvious that it was going to happen, but it's possible. Okay, but I definitely give them credit in the sense that I didn't know about these G functions until I read their paper. And then Alexander and I got really excited and we worked this out. That's pretty much how it worked. Okay, so let me, okay, so because Dan is in the audience, I'm going to make one more comment because I think it'll make him happy, and that's a significant goal in my life. That's true. That's true. So you're right. This is the PI, but there's Jacob. Okay, now you're going to make me spell his name. I think I know how to spell it. I think it's Zavatone Veth. He was the main author. That's right. Thank you. You're totally right. Okay, but like that whole group, including Jacob, they're all great. They do really cool stuff. Okay, I love their work. Okay, but let me say one other thing, which is that here I told you only about the posterior and not about the Bayesian evidence. So let me state as a final theorem. Okay, so if you do this, the same kind of thing. So suppose now you take everything to infinity, but what you do is you take P over N naught, alpha naught, and you just take L over N to some number lambda. So it's not P times L over N. So that P times L over N already went to infinity, but now I have this, which controls the prior. So then there exists a unique maximum for the Bayesian evidence, Z infinity of the data set, which depends only on lambda in the end. And it looks like this. So lambda star is, okay, it's the square root of 1 plus log squared of the norm of theta star over alpha naught minus 1. So it's one of these things where if you wanted to only get the right posterior, it doesn't really matter what value of L over N you chose in your prior, actually. It just has to be positive. But if you wanted to maximize the evidence, there is an optimal data-dependent ratio of depth to width that you need to choose. And so in this sense, I slightly lied. There's like these two different things. Do you want to make best predictions or do you want most parsimonious models? And if you want both, then you need to know both about L over N and about P times L over N. But if you only care about predictions, only P times L over N. So I didn't completely lie to you, Jim, but I lied a little bit. Okay, that's how I do it. Small omissions. Okay, so let me stop. I think I'm basically at the end. I'm happy to take questions or comments.
Two quick questions. So that capital star, is that related to like the norm of the input or something, or is it like, I mean, is it the critical value of the kernel?
Yeah. So right. Good question. I got lazy, but okay. Kappa star looks like this. It's the norm of theta star times 1 minus alpha naught over alpha naught.
Okay,
So in other, sorry, squared.
so it's something.
No, it has an easy interpretation in the following sense. Okay, if your data was generated like this, suppose there was some true parameter that generated your data, like some that you don't know. Then, like, what you actually see, right? Theta star is just theta true in my language parallel. You only see its projection onto the space of directions. And if you want to estimate what's the size of theta true perp squared, the best estimate you have for it is you say, well, I've observed its projection onto the span of the data. And so I'm first going to estimate the norm of theta star, and that's theta star squared, but you have to divide by alpha naught, right? If you've only observed half of the components, you should expect twice as big a thing. But then you have to project onto the perpendicular directions, so you deflate by 1 minus alpha. And so this is the value you get, and there's some like also maximum likelihood reason you get this value.
The other comment question was, I guess this is the relic of the fact that you're doing Bayesian inference and not gradient descent or something, but you might have expected the number of parameters to also be an important scale that shows up, but because you have L over N, like the number of parameters scaling very differently than the size of the data set. They're not,
that's right. And so for me, I wasn't 100% sure how different Bayesian inference would be from gradient descent, but precisely for the reason you're saying, I actually expect them to be rather different. And so I'd like to work out what gradient descent does, and I don't yet know, but it's like, it's kind of cool. Like what's going to be the,
I mean, I think there's an important scale where the parameters scale with the size of the data set size, but that's just a totally different regime.
Correct. So right. So there's people at Google Brain like Jeffrey Pennington and Ben Adlam who wrote a nice paper about that. Where in some random feature model, they see both the scales coming up and giving you different like peaks in your generalization error. It's really quite cool.
But for Bayesian inference, you can't see that because that's the scale where that scale is one where basically you're going to one corner of your phase vector.
That's right. That's right. So they do it for gradient descent, or more precisely, minimal norm interpolation. So gradient descent from the origin. That's right.
Hello, can you hear me?
There's a question online. Go ahead.
Yep. So if I were to set the same problem without the Bayesian inference and just try to solve the LSE or something, then the answer is going to be the minimum norm interpolant plus whatever component that was initialized in the kernel? Right?
No, not in this deep linear model. The reason is that, so if you have L equals 0, you're totally right. For linear models, what gradient descent does, if you start over here at theta naught, this is your original guess, you just project onto the space of interpolants. So maybe that's what you said. I didn't understand. When L equals 0, this is what happens.
Right. I was curious if the part that's initialized in the kernel evolves at all under, like, I don't know, gradient flow.
Yeah. So it does. That's the whole point. When you do gradient descent with these deep linear things, it still evolves in a non-trivial way, but no one exactly knows how it evolves. As far as I know, there's no formula. It's like kind of frustrating.
I see.
So it's not just a linear algebra operation anymore. You don't like project onto the space of interpolants. It's some thing which knows about the depth. Okay, I do this with my hands because I don't know what to write. Yeah.
Okay. All right. Thank you.
Yep.
Whereas it's awesome to have an explicit formula with these G's. Is there an intuitive understanding of what the answer is? Like if you say, oh great, I now understand my expectation values of all my thetas and moments and stuff like that, like what does it look like?
Okay, right. So I should have said this and I forgot. Okay, so the first thing to say is with non-asymptotically, there's no hope to have a better answer than like a contour integral in some sense. Okay, but asymptotically, I should have said this. So everything becomes Gaussian. And the reason is the following, right? Like if you take a random high dimensional unit vector, right, this becomes approximately normal. And so you have a delta function on the scale, and that just influences the variance of the predictions in the directions you haven't seen. So actually, so we get exact formulas for the posterior, but they're all asymptotically normal. And so you get the mean and the variance from these formulas, and okay, they depend on whatever they depend. So yeah, for sure. But I don't know how to better describe it than these G functions at finite sizes. There might be a good way to do it, and I haven't fully kind of digested that.
computation in each of the hidden layers, would the results, final results change too much because of the computation?
So the short answer is the final results in terms of the formulas, I have no idea if there is a closed form expression. I mean, it's like, honestly, for me personally, it was like a small miracle that it was possible to write things down exactly, even without the nonlinearities. I mean, it's rare to have exact formulas for posteriors, especially in some kind of nonlinear setting. Okay, that being said, you might still ask, is it true that it's like P times L over N that controls things? And okay, there's some hope for that, and I'm trying to work that out, but I'm really not sure. Like I would rather not speculate in a sense, because I also don't know how to simulate it effectively. Like sampling from these posteriors is so bad that like I don't trust anything that I see. So I feel like I have to do the calculation.
How is the choice of the Gaussian parameter distributions for generalization? So to get this close form.
Right. Okay. So it's a great question. So philosophically, it should be completely unimportant, right? Just like in random matrix theory, you have microscopic universality. As long as you match some moments of the Gaussian for your entries and they're independent, all the statistics should be essentially the same. So that's great. But then concretely in terms of the math, the point is that Gaussians are rotationally invariant. And we use that symmetry group very strongly. And that's what allows you to compute things in terms of these G functions. Like the fact that you get Gaussians and Bessel functions and spherical Bessel functions and blah, 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 whatever you normally get. Like the fact that you get them on the nose comes from the Gaussian. But I'm like completely sure that in these asymptotic regimes, you have universality in terms of the distribution of the entries. But I really don't know how to prove it.
At the risk of being annoying, I think if I recall Jacob and Jengiz's paper, they also actually compute the prior for ReLU networks, and it's like some sort of mixture over the deep linear answer, but for all the different widths, because you can imagine that
So that's actually not true. So they only compute at a single input. So Dan brings up a great point. This is one of my favorite things about this world. If you have a deep ReLU network, but a single input, it's exactly like a deep linear network where in every layer you zero out each ReLU with probability a half independently. So that's why you get all the possible widths and you get this nice answer. But as soon as you want to take P equals 2, done. So it's a little sad. It's a nice thing, but it's sad.
Okay, so that's why it's not trivial to generalize.
Yeah, exactly. Right. It'd be great if it were.
Great talk. Really fun to hear about this in person. Good to see you in person.
Thank you.
I'm just sort of the technicalities. I'm following along with some of the things that you're saying, but from the point of view, I mean, what is the trade-off here between sort of quality of the model and the ability to express it analytically? It is a miracle that you can compute the posterior like this, but is this like an ML version of a toy model that a physicist might think about, or what knowledge might you hope to extrapolate to more broad settings that you gained here?
So it's a good question. So I guess let me give two answers. I shouldn't speak for physicists. I don't know what physicists would say. Okay, but let me put it this way. For me, I wanted to understand what the joint effects of data set size, depth, and width are. And separately, they're understood a little bit. And I don't know any other place where they're understood jointly in an exact way. So I just wanted to see where the P fits in. Okay, so then it's like, okay, how similar are these deep linear networks, like qualitatively, to nonlinear networks? And the answer is, I don't know. But my feeling is if I can't compute it here, I'm totally screwed, right? So somehow, like, I was very happy about this. And now, like, I'm hoping to use some of the like similar computational things to do things asymptotically for nonlinear models and see if this appears or not. And that's kind of just the honest answer.
That's really, I mean, it feels very similar to the way we work. We sort of know what parameters we care about in the broad models, and then we simplify it to a toy model and understand it to death there, and then hope that extrapolates and study when it does extrapolate and when it doesn't.
Right.
That's where you're hoping to go, is to get a better sense of these.
Yeah, I am, but I'm not sure that this toy model captures all the relevant effects.
But it sounds like it's your first guess, because this is the only place you really.
Well, right, but first and also last, that's the problem, you know. But if only I had some more data points, that would be great. Right.
Thanks a lot, Boris.
Yeah, for sure. Thanks, Jim.
I guess in the spirit of this question, how do you empirically even check whether any of the theory extrapolates to nonlinear networks? Do you have any sort of like ideas?
Yeah, so right. So it's really hard to do Bayesian inference like on a computer for extremely large networks, obviously. But you could do two things. One is you could say maybe gradient descent in some regimes is not too different from Bayesian inference. And then you could do gradient descent and see if it has high likelihood under your posterior. That's like a thing you could try. And beyond that, like, I don't know what to say. Like, for me, the whole point of doing Bayesian inference is you don't need to like do the simulations. You can hopefully just sample from your analytic closed form of the posterior or some variational approximation. You don't have to worry about it. But I get where you're coming from. It'd be nice to check for nonlinear networks exactly what happens. And we were unsuccessful in having anything that convinced us one way or the other. So yeah, I don't know what else to say. Sorry. Oh,
Well, we'll take one more question.
don't forget about the reception.
That was the next line. Yeah.
Thank you. A great job. This is sort of a hypothetical question. Is it possible to write the linear activation functions as many combinations of cosines and sines and get the final closed form expressions corresponding to those sine and cosine modes in this particular case? Because the paper by Pelaban and Javaton did something similar, if I remember correctly.
Okay, so the short answer is I don't know. I mean, like, if I were to interpret what you're saying a little bit, in my own way, you might say, can you do perturbation theory one way or another around the linear regime?
Right.
And like, I'm working on that. I'm trying, but I really don't know. Like, am I going to get exact formulas? Am I going to get like asymptotic formulas? Am I not going to get anything because I don't know how to compute some integral? I mean, that's like half of my life, I feel like, right? No, right. I mean, like you don't always succeed. So I don't know. Yeah.
That makes sense.
All right, let's thank Boris again for visiting and for giving us a talk. And we can continue harassing him with questions 2 stories up.